Alright class, let's delve into the fascinating world of atoms. We'll be discussing hydrogen atom and quantum numbers. The hydrogen atom is the simplest atom in nature and therefore a good starting point to study atoms and atomic structure. The hydrogen atom consists of a single negatively charged electron that moves about a positively charged proton. Now, this simple structure, one proton and one electron, might seem unremarkable, but it's fundamental. Understanding the hydrogen atom is crucial because it's the building block for everything else. All other atoms are built upon this basic principle. Now, the concept of quantum numbers, which describes the position, shape, and energy of electrons in an atom. These quantum numbers help us understand how atoms behave, form bonds, and create the world around us. Basically, it helps us describe the electron's properties more precisely. These numbers tell us about the electron's energy level, the shape of the orbital, and its orientation in space. They are essential for understanding how atoms interact with each other and form molecules and basis of all matters. So, what is an atom? Everything in the universe, from the smallest speck of dust to the largest star, is made of matter. The fundamental building blocks of all matter is atom. An atom is the smallest unit of an element that restrain the chemical properties of that element. So, atom consists of a central nucleus containing positively charged proton and neutral neutrons, surrounded by a cloud of negatively charged electron. We'll explore the properties of the subatomic particles in more detail on the next slide. The arrangement and numbers of these particles determine the unique characteristics of each element. Now that we've established the basic concept of the atom, let's examine its key components in more detail. As you can see in the PPT, the atom isn't just a solid mass, it has a complex internal structure. First, we have the electron cloud. This isn't a literal cloud, of course, but a region surrounding the nucleus where electrons are most likely to be found. Electrons don't orbit the nucleus in neat circular path as depicted in older models. Their behavior is more probabilistic, described by the quantum mechanics. Within this electron cloud, electrons reside in specific three-dimensional regions called atomic orbitals. These orbitals are not fixed path but represent the probability distribution of finding an electron at a given point in space. They come in various shape, energy levels, influencing the atom chemical properties. And finally, we have the electrons themselves. There are negatively charged subatomic particles that occupy the atomic orbital surrounding the nucleus. The number of electrons in an atom usually equals the number of protons in the nucleus, resulting in a neutral overall charge. Now let's continue. At the center of every atom is the atomic nucleus. This is the atom's positively charged core. Inside the nucleus, we find protons. These are positively charged particles. The number of protons determines the element the atom is. For example, 1 proton means it's hydrogen, 2 proton means it's helium, and so on. Along with protons, the nucleus also contains neutrons. These particles have no charge. They are neutral. Neutrons contribute to the atom mass but don't affect its charge. Finally, orbiting the nucleus are electrons. Now we tackle this kaganina. These are negatively charged particles. They are much smaller than protons and neutrons and move around the nucleus is what would we call electron shells or orbitals. So to summarize, atoms are comprised of a central nucleus containing positively charged proton and neutral neutron surrounded by a negatively charged electron orbiting in shells. The arrangement and numbers of these particles define the properties of each element. the hydrogen atom in detail, comparing older models with our current understanding based on quantum mechanics. Let's start with the basic. Hydrogen, the simplest atom, possesses a remarkably simple structure, one proton and one electron. Unlike many other atoms, it contains no neutron. In simple diagram, no, the illustration, the atom's component, we have the nucleus containing the proton and the electron orbiting it. Early models like the Bohr model depicted electrons orbiting the nucleus in fixed, no, defined paths much like planets orbiting the sun. This is a planetary model. The Bohr model, while simplistic, provides a framework for understanding electron energy levels and transition. The equations shown here allow us to calculate the change in energy during electron transition between different energy levels. However, it has limitations. Modern quantum mechanics offers a more refined perspective. Electrons don't follow predictable paths but exist within the probability distribution called orbitals. These orbitals represent the regions of space where an electron is most likely to be found. This diagram shows the shape of various orbitals. These aren't solid shapes but represent probability density, like likelihood of finding an electron or particular location. The s orbitals is spherical while p orbitals have a dumbbell shape. More complex orbital exist, but the basic idea of probability distribution remains central. So the hydrogen atom, while seemingly simple, no, showcase a transition from classical planetary models to the more accurate probabilistic description offered by quantum mechanics. This fundamental shift in understanding is crucial for comprehending the behavior of all atoms and molecules. In our previous discussion, we've seen how the Bohr model, while useful, provided an incomplete picture of the hydrogen atom. It couldn't accurately predict the behavior of more complex atoms. That's where the Schrödinger equations comes in. The time-independent Schrödinger equation shown here is a cornerstone of quantum mechanics. Unlike the Bohr model, it provides exact solution for the hydrogen atom. It doesn't just describe electron orbit, a simple path. It reveals the energy levels and wave function of the electron. This equation might seem complex and it is mathematically sophisticated, but fundamentally, it describes the electron's behavior in terms of probability. The solution represents the wave function, which gives the probability of finding the electron at specific location, which is the R around the nucleus. The Schrödinger equation is crucial because it accurately calculates all allowed energies and wave function for the hydrogen atom. This is a significant improvement over the Bohr model. Solving this equation for the hydrogen atom is a fundamental step in quantum chemistry because it provides a foundation for understanding more complex atoms and molecules. The equation solution gives rise to the shape of the orbital we discussed earlier. Now, let's discuss how we describe an electron's location and energy more precisely using quantum numbers. First, we have the principal quantum numbers, the n. This defines the electron's energy level. It's a positive integer n, can be 1, 2, or 3, and so on. Higher values of n, or the quantum number, indicates higher energy levels and greater distance from the nucleus. Think of it like a shell in the Bohr model but with a probable interpretation. Next is the angular momentum quantum number, or the I. This dictates the orbital shapes. No? We can have integer values ranging from 0 to -1. The quantum number equals 0 corresponds to an s orbital or spherical, and 1 to a p orbital or the double shape, I equals 2 to a d orbital or d orbital, and so on. Each value of the I represent a subshell within a given energy level. In total, four quantum numbers are needed to completely describe the state of a single electron within an atom. This number uniquely identify each. This is the Pauli exclusion principle. No two electrons can have the same set of four quantum numbers. We've covered two of them, N and I. The remaining two, the magnetic quantum number or ML sa inyong makita, and the spin quantum number, which is MS, specify the orbital orientation and electron spin, which we can discuss later. So, quantum numbers provide a precise way to describe the state of an electron within an atom, moving beyond the limitation of classical models. They are essential for understanding atomic structure and chemical bonding. Now, let's complete our discussion of quantum numbers. We've covered the principal quantum numbers and the angular momentum quantum numbers. Two more are needed to fully describe an electron state. The magnetic quantum numbers, or the makita ninyo is ML, determines the orbital orientation in space. Its values depend on the I. They range from negative to positive, including 0. For example, if the I equals 1, no, p orbital, no, ML can be negative 1, 0, or positive 1, no, representing three different p orbitals oriented along the x, y, and z axis. The spin quantum number, MS, no, sa inyong makita, describe the electron's intrinsic angular momentum or iyahang spin. It's an intrinsic property of the electron, like its charge. It can only have two values, positive 1/2 or negative 1/2. These represent the two possible spin orientation of the electron. This brings us to the crucial principle, the Pauli exclusion principle. This principle states that no two electron is an atom, no, can simultaneously have the same set of four quantum numbers, not the N, L, ML, o MS sa inyong makita. In simpler terms, each electron in an atom must have a unique quantum state. This principle is fundamental to understanding atomic structure and the arrangement of electron in atoms. It explains why electrons fill orbitals in the way they do and why atoms have chemical properties, no, as they do. Therefore, the four quantum numbers, no, the principal, angular momentum, magnetic, and spin, completely define the state of an electron within an atom, ensuring that each electron occupies a unique quantum state. This is the key concept in quantum mechanics and is essential for understanding chemical behavior.